Hello, calculus fans. All right, let's suppose we're going to invest $10,000 at 6% interest. This is going to be compounded annually. That means that your interest is being withheld until after a year. It is paid out in a lump sum at the end of 1 year. And then after 1 year, our investment is going to be worth 10,000 times 1.06 to get 10,600. So we're adding on the 6% interest. After 2 years, you get to earn interest on your interest. So now you do 10,000 times 1.06 and then multiply again by 1.06. And we'll get $11,236. So in general, after t years, we can say that it's worth 10,000 times 1.06 to the t power. And even more generally, we can say that if we have an amount P, a principal amount, and it's invested at an interest rate R, after t years, it's going to be worth an amount of P times 1 plus R to the t power. Now, normally, interest is compounded more frequently than that. Let's say n times a year. So then in each compounding period, the interest rate is R over n. And there are n times t periods in t years. So maybe you can think about what happens if you compound every quarter. So then the interest rate is R divided by 4, and then there are 4 times t periods in t years. Then after t years, the value of the investment looks like this. A is equal to P times 1 plus R over n, all raised to the nt power. Now, we want to increase the number of compounding periods. If we do that, then the amount of interest will increase. And if we let n approach infinity, then we're going to be compounding the interest continuously. And in that case, the value of our investment is going to look like this. There's going to be a limit as n approaches infinity of P times 1 plus R over n to the nt power. Now there's some algebraic tricks we can run into here. We're going to change it so that it looks like this. Now you should see that we have actually the same thing, because when you have a power on top of a power, you just multiply the powers. And so that's how it's going to come out to be n times t. We can pull the p outside the limit. And then we can make a substitution to let m be equal to n over r, in which case this exponent just turns into m, and this fraction turns into 1 over m. And now here's the key. This piece on the inside here has a limit, and it's e. We've seen that one before. So our answer is that we get p e to the rt. So this is the general formula for continuously compounded interest. Let's go through an example to see how we use this. All right, suppose we invest $10,000, 3% interest, for 30 months. The interest is going to be compounded continuously. The question is, how much will we have at the end of the 30 months? And then as a follow-up question, we'll ask, how long does it take for the money to double? So we're using R equals 0.03, that's the 3% interest. We're using T is equal to 2.5 because that's 30 months measured in years. So our formula, if the interest is given as annual interest, then we have to use our time in terms of years. The initial amount is 10,000. So according to our continuously compounded interest formula, we're going to get that the amount is 10,000 times e to the rt. R is 0.03, t is 2.5, and this works out to about $10,000, $10,778.84. Our follow-up question was, how long does it take for the money to double? We'll just plug in A equals 20,000. That's when we'll have doubled our investment, and then we'll solve for t. So 20,000 is equal to 10,000 times e to the 0.03t. Divide by 10,000. Take the log of both sides, and then divide to get t. That works out to about 23.1. So if you're only earning 3% interest, it takes a little over 23 years to double your investment. Okay, that's all for now.